Welcome to homework.
In this problem, we have a bar bent into an L shape that's cantilevered at one end, and then there's a load acting, distributed load that's uniform, acting over the entire length of the bar that's into the plane here. So first, this is where I'm going to take it away from the clamp, so I have an internal force and an internal moment, and they'll generally have, again, three components each. Now we can make an equivalent point load, and I guess I should maybe kind of draw that here. We can make one for this region, and an equivalent point load there, and an equivalent point load here for these distributed loads. And so this one here is minus 16 pounds in the z direction, and this is minus 8 pounds in the z direction. The position vector to this one is 2 feet in the y, and to this one is minus 1 foot in the x. Again, x is this way, y is this way. Minus 1 foot in the x and 4 feet in the y. Summing forces basically just says that this force here has to be negative of these. So that means it's 24 pounds in the z direction. If we sum moments, then we get moments from these two loads, and again we can take the cross product of this and this, and then this and this, and that will be equal to the negative of what this moment is. And it turns out that that winds up being 64 foot-pounds in about the x-axis, so that's a bending moment, and 8 foot-pounds about the y-axis, so that's a twisting moment. So this beam is acting to bend it in the z direction, bend this bar in the z direction, and also twist it. Now we want to look at internals, so we take a cut at an arbitrary position here, and so we take this cut, and we know we have these values, and we're looking for these values. So the equivalent point load here is going to be minus 4 times y, where y is measured from here. So that's the distributed load has a magnitude of 4 pounds per foot. The position vector to here is y over 2 in the y direction. Now we can sum moments, or sum forces, and we know what this is, and now we know what this is, so we can solve for this. And it turns out that this is just minus 24 plus 4y pounds in the z direction. And for the moments, we can take our moment balance, and we have this moment plus the equivalent moment from the, let's see here, I took moments about this point. So then the equivalent moment, so we have R1 prime and P1 prime crossed with those two. Then this moment, and then the moment caused by this internal load, and that acts at a distance y from this point. So we need to take this vector, position vector, cross with n. Doing all that, and solving for m, we see that m is minus 64 plus 24y minus 2y squared in about the x-axis. So this is the bending moment. And we can see that, let's see when, so then obviously this moment actually is, the magnitude is the maximum here, and then it decreases as we go out. And then the shear about the z-axis, so this is the shear. The shear is still just a constant because this load here doesn't actually contribute to the shearing. It's actually only the load that's out here that's contributing to the shearing. So that the load here, actually we could think about this load, this distributed load out here on this part, as actually just providing a torque about a twisting moment about this beam. So this is basically just a twisting moment, and not we want to twist the whole thing. And that twisting moment is a constant, as you no matter where you are in this section of the beam.